Hello, my name is Leandro Schemmer. I am a student at Coursera, and this is my final project for the course, Managing Machine Learning Project. I appreciate everyone watching, and I hope that you enjoy this time. Project definition: computer vision-based identification of defects in the finish of toy cars. Problem description and context. A toy company wants to implement an AI-powered defect detection system. Currently, toy inspection is done visually. A human inspector visually checks the product against a reference image from the project. This process can be slow, exhausting, and imprecise, making it prone to human errors, inspector distractions, fatigue, and other limitations. Opportunity for machine learning. Computer vision can detect defects in real time in a systematic, detailed, and objective manner, without being affected by subjective factors such as mood, fatigue, or distraction. But is this important to anyone? Absolutely. This is crucial for the end customer who expects a flawless product with a perfect finish, especially collectors. It is also essential for the manufacturing company, as reducing customer complaints improves customer relationships and fosters brand loyalty. Defining the problem. Target users. Toy manufacturing companies seeking to enhance their quality inspection process with automated technology. Problem statement. Currently, quality inspection relies heavily on manual processes that are time-consuming, prone to human error, and may fail to detect defects that impact the final product's quality. Why does this matter? Undetected defects reach the end consumer, leading to disappointment, stress, and frustration, ultimately damaging the manufacturer's reputation and potentially losing customers. Additionally, manual inspection can be inconsistent, causing variations and dispersion in product quality. How is this problem currently addressed? Through visual inspection by production inspectors using 3D rendered reference images. Gaps in the current system. The manual nature of the system makes it highly prone to inaccuracies and unnecessary delays, with variations in inspection time due to a lack of standardization. Defining success. Expected business impact. Reduction in inspection time. Increase in defect detection rate compared to manual inspection, thereby reducing customer complaints. Constraints. The model must be fast enough to operate in real time or near real time. It must be trained to recognize different types of products and a wide variety of defects. The system should be accessible to companies without large teams or AI specialists. Success metrics. Initial reduction in inspection time compared to manual inspection. Increase in defect detection rate compared to the manual process. Reduction in the relative number of customer complaints in the field. Identification of factors. Expertise. Requires knowledge of defect types in products. Understanding of computer vision techniques. Experience in optimizing models to run in real time. Relevant factors. Quality of the collected images. Proper lighting on the product. Clear definition of what constitutes a defect. Sufficient data volume available for model training. Solution validation plan. The proposed solution consists of a computer vision system based on machine learning to automatically detect defects in industrial products. The model will analyze product images captured by cameras at the end of the production line, classify whether a product contains defects, and indicate their location. The system will compare a photo of the toy car with a 3D rendered image from the project. Operation. The toy car is positioned on a platform where photos are taken from 6 angles: bottom, top, both sides, front, and rear. These positions are standardized and fixed using mechanical devices to minimize variations. A strategically placed fixed light source ensures proper illumination. The photos undergo pre-processing, where the background is removed and images are separated into their 3-color channels. The same process is applied to the rendered images of the 3D model. Real-time evaluation. The system searches its database for the most similar car model from ongoing production projects and compares the captured image with the reference image. If no defects are detected, the system approves the toy car. Otherwise, an alarm is triggered, and the detected defect is displayed on screen for the human operator. Iterative experiments to validate the proposed solution concept. Training. The system must detect defects in toy cars by comparing two images, the 3D rendered project image and the real-world image. To achieve this, a dataset is created with multiple images of different toy cars, where a series of defects are artificially introduced in the 3D CAD model. For example, removing a headlight, a wheel, or a window. Adding paint defects. Removing doors or bumpers, misaligning or bending the license plate. Additionally, physical toy cars are produced with intentional defects, such as scratches, dents, missing or misaligned parts, etc. This dataset is then split into a training set and a validation set to train and evaluate the model. Continuous improvement. The initial goal is not to fully replace the human inspector, but rather to enhance productivity and reduce errors. The system is continuously improved based on inspector feedback, ensuring ongoing learning and adaptation. If a defective toy incorrectly passes inspection, or if a non-defective toy is rejected, this feedback is used to further train the model. Over time, this process generates new data, refining and improving the model's accuracy. Main project architecture. 3 key decisions are crucial for this machine learning project. Cloud versus edge computing. The edge solution was chosen. The production line cannot afford downtime due to cloud connectivity issues. Additionally, data privacy is a major concern. The company enforces strict security policies and does not want its projects to be sent to external servers. Offline learning versus online learning. Online learning was selected. With continuous feedback, the system can immediately or nearly immediately improve by learning from newly detected defects. This allows for rapid adaptation and refinement. Online predictions versus batch processing. Online predictions were chosen over batch processing. The inspection process must detect defects in real time, ensuring defective products are immediately removed from the production line without delays. This is critical in case of systematic errors in production that were not detected in the initial training phase. The system does not need to wait for image batches and can continuously improve with each new image. Potential risks in production. Training distortions. The initial training dataset is inherently limited by the imagination of professionals creating the database, as well as by the cost and time constraints associated with generating defect samples. It is practically impossible to include all real-world defect variations in the initial dataset. If the actual defect configurations significantly exceed what was initially anticipated, this may frustrate users and even compromise the system's adoption. This is why continuous learning through production line feedback is essential. Excessive latency. The system must be fast, ensuring real-time inference without delays in inspection. Therefore, the model needs to be highly optimized, avoiding brute force approaches that require excessively large models, which could slow down performance. Data drift. Changes in materials, lighting conditions, or reflections can alter image characteristics in unexpected ways. For example, a new type of paint or a specific surface curvature may reflect light differently, causing saturation effects that confuse the model. This may require camera adjustments, improved filtering, or repositioning of light sources. Additionally, product variations may lead to confusion. For instance, the company may introduce a toy car designed to look old and worn out, featuring intentional asymmetries and defects. Despite having a reference image, the system could mistakenly classify these intentional characteristics as actual defects. Concept: drift. The definition of a defect may evolve over time. Tolerances in alignment, surface finish, or minor imperfections could change based on product line requirements. For example, budget-friendly toy lines might allow for greater defect tolerance, whereas premium products require stricter standards. Model bias. The camera angles and lighting setup may highlight certain defects while making others less noticeable. This could lead to uneven defect detection performance. To mitigate this, the system must be statistically evaluated. That's it. The presentation is over. Thank you very much for watching.